we have Dr. Bach Nguyen. He's from Xavier University of Louisiana, and we know Bach Nguyen about 3 years ago, right? Yeah, and we met him.
We met
a
few years ago.
Scholar. Yeah, and recently he just got a tenure track job at Xavier University of Louisiana. And thank you, Bach, for agreeing to give talk here. And today he will give talk on a topic of friendly introduction to cluster algebras.
Yeah.
So your time,
thank you very much for the introduction. I also thank you, the organizers, for the invitation. I'm very happy to be here to give a talk in the Trojan Math Seminar. And also to thank you everybody for attending the talk. So this talk is basically a very a brief introduction to cluster algebras. I'm not going to give a technical definition of what is a cluster algebra, but rather I will go over a sequence of motivating examples to illustrate why cluster algebra is interesting. Okay, so let's. I move the page. I just go down. Okay. So first is an outline. So we'll mention briefly what is the history and application of cluster algebra. Then we move on to some motivational examples, and then we'll discuss a very general type of cluster algebra called cluster algebra of geometric type. And then I will tell you a little bit about what my current research interests are in the area of cluster algebra. Okay, so let's start with some history of application. Okay, so it's supposed to so when you click, or it's a beamer, so when you click, you move to the next slide. But here I'm on an iPad, so I have to scroll it up and down, so it doesn't look very smooth. it's very all right. Okay, so history and application. So first, this object cluster algebra was introduced in the beginning of 2000 by Sergei Fomin and Zelevinsky. The purpose of their work to introduce this object is to study this thing called a canonical basis and the phenomenon called positivity conditions in Lie theory. Yeah. But since then, the math community was welcomed in this new object, cluster algebra, very good. It developed is very private research area. It's become a very private research area, and many very interesting examples. So in particular, here's a small diagram of where cluster algebra is applied to, and then where is it connected to. So in particular, it's connected to knot theory, topology. Certain knot invariants can be described in the language of cluster theory. This is connected to Poisson geometry due to the work of Alex Feinstein, Michael Shapiro, and Michael Geckman. So these people developed a cluster theory that involved Poisson geometry. And also is related to techmolar theories, algebraic geometry, mathematical physics, in particular in terms of the dynamical system or discrete dynamical system, to be specific. Okay? And heavily cluster algebra is heavily influenced in algebraic combinatorics. Many interesting problems in algebraic combinatorics is use cluster algebra and has application in cluster algebra. Okay? Representation theory of algebras, Lie theories, which I mentioned earlier, the original purpose of cluster algebra to solve problems in Lie theories. So many areas in mathematics is touched by cluster algebra. Very interesting subject. So this is some of the history and application of cluster algebra. So now let's just move on to some examples where cluster algebra happens naturally. Okay? So this object, this example I'm discussing here, it would work before cluster algebra was invented. Okay? So let's see. The first example, the first motivational example I will discuss is something called freeze patterns. The freeze pattern. So what is a Friese pattern? Okay. It's defined by Coxeter in the early 70s. So a Friese pattern is a grid of integers. Okay, it's a grid of integers, positive integers to be precise, where the rows are infinite in both ends. It's infinite rows in both ends. Okay, so something look like this. Oh, not yet. Well, the original purpose of Friese patterns, Coxeter was using it to study something called Gauss was related to Gauss, called Gauss formulas for miraculous pentagrams. Okay, so that was the original use of Coxeter Friese pattern by Coxeter. Okay. And not just that, but after that, it's been found to be related to something called cross ratios, continued fraction, Fourier series, and triangulation of polygons. Okay. So this is a very interesting topics on its own, and it's a connection to Friese pattern. Okay. And more recently, Friese pattern has been used to study representation theory of finite dimensional algebras, using language of categorical categories, categorical languages to describe representation theory of algebras. Okay. So now let's see an example of a Friese pattern. So a Friese pattern. So in this example, we describing a Friese pattern of order n, where n is 5. So the order of a Friese pattern would be the number of rows. Add 1 to it. Okay. Where the top and the bottom rows are rows of ones. Okay. Every entry in the rows is 1. Okay. So let's see. So this is something. This is what the Friese patterns look like. Okay. So you have 4 rows. Right? So the order is n plus 1. 4 plus 1 is 5. So this is an example of a Friese order, Friese of order 5. Okay? So the top rows and the bottom rows is are rows of ones, and the middle 2 rows are some positive integers. Where the rules to fill in these entries are as follows. So if you have any 2 entries, any 4 entries of the following shape, I think I can write on here. So A, hang on. So if you have entries that have the diamond shape, so what I mean by that is something like this, A, B, C, and D. Yeah. Something like this, right? So for example, this shape, for example, right? That's a diamond shape, and A is right here, and B is here, and C is here, and D is here. Okay, then you would have AD, A times D equal to B times C plus 1. Okay. Right. So let's check. So 1 times 2 is 2. 2 is equal to 1 plus 1, right? If you take this one, here's 4, here's 3, right? So satisfy this relation. Yeah. Okay, so that's the rules for filling in the entries, the rows in the middle. Okay. So any questions on this example so far? Please let me know. Okay. Okay. So now what do we do with this? Let's observe. Let's make some observation. So let's look at this. So first, look at this shape from here to here. Let me draw this. Okay. Look at this shape here. You notice these entries. The entries in this shape. You have 1, 2, 3, 2, 1. Right. This one, 1, 2, 3, 2, and 1. Okay. And then you look at the one next to it. This shape right here. It's going to be a 1 right here. And you have 1, 2, 3, 2, 1. So it's been inverted. Right? So this shape. So this is the patterns. Right? the whole freeze pattern is this kind of shape repeated. It's periodic. You take this shape, you reflect it, and then you glide it to the left or the right. Okay. So that's the pattern in this freeze. Okay, so this is a small example of a freeze pattern for the 5 with the rules. It's AD plus equal to BC plus 1. Okay. And it has this following periodic patterns system. So in each cycle, we call this thing a cycle. Each cycle you have 4 non-trivial entries. Okay, three non-trivial entries. 1, 2, 3, okay. And the others entries are repeated of those. Okay. So let's move on to the next example, and we see in more details this phenomenon. Okay. So one remark is that the entries of the freeze I can take to be from any unital rings, not just integers. Okay. A ring of integers is unital rings. So I can, instead of using integer, I can use any unital rings and use the entry from that rings to put in the freeze pattern. Okay. In particular, we will consider things from the ring of polynomials in one variable or multiple variables over the integers or over the rational numbers. Okay. So things become more interesting if you, instead of using integer, you put in polynomials into the entries. And the next example, we will see such a case. So here, the next example, I will still consider a freeze pattern of order 5, but a more general rule. Okay, a more general rule. So the earlier rule was AD equal to BC plus 1. Okay, every time I have a diamond shape, I enforce this rule. But now I will consider a more general rule than this. Okay? So for this, okay, in this freeze, order 5, the top and the bottom rows are trivial rows consisting of ones. In the middle rows, I put in a variable x1, x2, x3, x4, x5, and so on in this way. Okay, where xk here, so indeterminates variables, and the rules that I'm imposing on the entries like this. Okay. So every diamond shape is still a diamond shape, right? x1 times x3 is equal to 1 times x2 plus 1 to the d1 plus 1. If so, here k here would be 2, is even. Okay, k would be in this diamond shape is k is 2, even. So I would use d1. Okay. So x1 times x3. x1 times x3 is equal to x2 to the d1 plus 1. Okay. If I want to take this one, and this would be k here is equal to 4. Yeah? And I get x3 times x5 is equal to x4 to the d1 plus 1. Okay. Where d1, d2, right? d1, d2 here are integers. Okay. You want a positive integer. Okay. All right. Let's do an odd one. So if I take, let's use a different color. If I take this one, for example, right, then that k would be odd. This is k is 3 here. Okay, so I have x2, x4 equal to x3 to the d2 plus 1. Okay. Right, so this is the new rule, right, that describing that dictates how you put in the entries of the freeze. Okay. Compared to a previous rule, right? So D here would be 1, and D1, D2 is 1, and the entries are integers. Right? I evaluate these variables at integers 1 and 2. Okay? But here I don't evaluate the variables. I just leave them as an indeterminate, and D1, D2 could be values. Okay. So this become more interesting. So let's just consider the following: solving for all the variable xk. Okay, if we choose to fix x1 and x2 first, right? Let's suppose that we fix x1 and x2, and let's try and solve everything else in terms of x1 and x2. Let's see if we can do that. So it's turned out that we can, right? We can. If we make the choice for x1 and x2, then every other xk can be written in terms of x1 and x2. Okay. Okay. So let's consider a small example where d1, d2 is 1, 1. Okay. d1, d2 is 1, 1. Let's compute the xk. Okay. So x3, right? x3 is going to be so you look at the diamond. So let me go back to the freeze. So x3, right? x3, x1 times x3 is equal to x2 to the d1 plus 1. Okay, x1 times x3 is equal to x2 to the d1 plus 1. But d1 is 1, so it's equal to x2 plus 1. Okay, x2 plus 1. Okay, so I have this equation. So I can solve x3 in terms of x1 and x2, and I get this. Okay, so x3 is x2 plus x1 over x1. X2 plus 1 over x1. Okay. Okay. So you do that. You for x4, same thing. You do the same method for x4. So x2 times x4 is gonna be x3 plus 1. So you solve it for x4, you get this. x1 plus x2 plus 1 over x1 times x2. And you keep repeating the process, and you get x5. x5 is x1 plus 1 over x2. And then you get to x6 and x7. You solve for x6 and x7 and similarly as before, and you get x6 equal 1, x1, and x7 equal x2. So the cycle stops. Right? So that's completed cycle. So every cycle is go from x1 all the way to x5, and then it's repeat. Okay. So a cycle here would consisting of x1, x2, x3, x4, x5, and it stop, and then the new cycle repeat with the same set of variables. Okay, and every variable is written in terms of x1 and x2. Okay. Now let's make some observation here. Look at this. This rational polynomials in terms of x1 and x2 that describe in x3, x4, and x5. Okay. This is what we call a Laurent polynomial. Okay. So these things are in the maybe I should write Q. Oops, no, wrong one. Sorry about that. Let's see, where was that? Here. So these elements, this rational polynomials here in Z, x1, x2, x1 inverse, x2 inverse. Okay. So we call this ring a ring of Laurent polynomials. Right. And also notice that the coefficient of these polynomials, these Laurent polynomials, they are positive. This is not a coincidence. This turned out to be a very difficult fact that's just been proven in 2010, I believe, that the Laurent polynomials, this variable x k can be expressed in terms of a Laurent polynomial, in terms of x1 and x2, and the coefficient are positive. Okay. So that's the observation I just mentioned. Xk expressed as Laurent polynomials in terms of x1 and x2, whose coefficients are all positives. Okay. And another observation, as I already stated, that the entries of the frieze are described by cycles consisting of x1 to x5. Okay. Now, this, if you take the entries x1 to x5, right? These are Laurent polynomials in terms of x1 and x2 only. Right? You take these elements, you generate an algebra, a Z algebra, right? a Z subalgebra over the ring of rational polynomials Q x1 x2. Okay. This algebra is an example of what we call a cluster algebra. Okay. So this is a natural occurrence of cluster algebra in work that appears before cluster algebra. So to restate, the algebra here is you take the G subalgebra of Q x1 x2 generated by these elements. I circle in blue. Okay. All right. So then next example, let's consider the case of D1, D2 is 1, 2. Okay. So before we consider the example of D1, D2 is equal to 1, 1. Now let's do an example where D1, D2 is 1, 2. Okay. So what happened in the case of 1, 2? Let's see. You can carry out the same computation, and you will see that x3 is equal to x2 plus 1 over x1. Okay. And so on, x4, x5, x6, are all Laurent polynomials in terms of x1 and x2. Okay. And all the coefficients are positive. Okay. And then when you get to x7, you return back to x1, and x8 return back to x2. So the cycle stops at x6. Okay. So the cycle consisting of x1, x2, all the way to x6, and it stops, and then it's repeat. So this is the case for D1, D2 equal to 1, 2. Oops. So same observation can be made here, right? All this xk expressed in terms of x1, x2 as a Laurent polynomial in the term of x1, x2. And all the coefficients are positive. And the cycle is from x1 to x6, consisting of the cycle, or one cycle. Okay. So this Laurent being expressed as Laurent polynomial here, what people in cluster theory refer to as the Laurent phenomenon. And all the coefficients are positive, what we're referring to as the positive, or these two very proved, and it's only been proven recently for cluster algebra in 2010 or so. For the next example, still have one more observation. So again, you take the Z subalgebra of Qx1, x2, right, the rational polynomial of x1, x2. Take the Z subalgebra of that generated by this Laurent polynomials. Okay. And that would give you an example of a cluster algebra, what we call a cluster algebra of finite type. Finite here is has a meaning. Y is finite, and we will see why in a moment when we introduce some more terminologies. Okay. So here's a theorem summarized in this example. So it only happens that you have a cycle and periodicity when D1, D2s are of the three cases, 1, 1, 1, 2, and 1, 3. Right? And you only have cycle and periodicity only in these three cases. Okay. And any other case, any other kind of values for D1 and D2, you get something else called cluster algebra, infinite time. Okay, you won't have a cycle anymore. You would have x1, x2. You fix them, and then you get x3, x4, x5, so on. You won't stop. It won't stop. But everything's still able to be expressed as a Laurent polynomial in terms of x1, x2, though. So the Laurent phenomenon still hold. But instead of getting a finite cycle, you get an infinite. I'm not sure who to credit this theorem to, but I'm pretty sure somebody in the original, in the beginning of the theory, I guess could be going to Fomin and Zelevinsky. There's another remark is that this is very interesting connection between freeze patterns and triangulation of n-gons. So what I mean by triangulation of n-gons, if you have a n-gon like this, you can cut it into triangles. Okay? So this is this what I have here is an example of triangulation of n-gons into three triangles, 1, 2, 3. Okay? So there's a connection, there's a correspondence between the freeze pattern and triangulation of n-gon. And this triangulation of n-gons would also give rise to examples of cluster algebra of finite time. So this right here, this theorem here, doesn't give you all the cluster algebra of finite time. It's only give you 3, which is related to freeze patterns. Okay. But the triangulation of n-gons will give you all the cluster algebra of finite time. Yeah. So that's freeze pattern. Before I move on to the next one, anybody have comments or questions? Okay. So for the next motivational example, I will talk about something from number theory. Okay? So this thing we call a Markov triples. Okay, Markov triples. So what is a Markov triple? So it's a triple of positive integers. I call it x1, x2, and x3. Which satisfies equations where you sum of xi squared equal to 3 times x1 times x1, x2, x3. Okay. Okay. There's a triple of positive integers that satisfy these equations. So, for example, what would be a Markov triple? You can take 1, 1, 1. Right? 1, 1, 1 satisfy this equation. So that's a Markov triple. 1, 1, 2 also. 1, 5, 2 is also a Markov triple. Right? So it's a fact that there's infinitely many Markov triples. So how is this related to cluster algebra? Okay. So turn out the solution of the Markov equations, they come from the cluster algebra. They are element in the cluster algebra, evaluated as certain integers. Okay. So if I start with this one, the Markov triple, right? I take some specific element in the cluster algebra and I evaluate at 1, 1, 1, and then apply some process that is described in cluster algebra, cluster theory, which we'll be discussing in a moment, and I will get a new solution of Markov triples. Okay. So Markov triples or Markov equation, Markov solution or solution to Markov equations, they are coming from elements of cluster algebra, some specific cluster algebra. Okay.
Excuse me, but may I ask you a question?
Yeah.
I just wonder the coefficient 3 on the right hand side part. Why is it 3?
Oh, I'm not sure the history of Markov equation, but yeah, this is 3. Yeah, I guess because 3 variables. I'm not sure.
So here we have triple, right? If you increase the number of variables like x1 square, x2 square, x3 square,
see. You mean
x4 square, so you get 4x1, x2, x3, x4. Yes,
something
yes,
like
yes.
this?
Yes, yes.
I see. Perhaps there's something in the literature called generalized Markov sequence, maybe. I'm not sure. Yeah, but you're right. This could be interesting equations. Yes, this could be very interesting Diophantine equations. Yes, but I haven't looked up this yet.
Okay, thank you.
Thank you for the questions. I think this could be very interesting equation. This might be related to something I learned a while ago. We can talk afterward. Yeah. So this remark here is what I just mentioned earlier. So there are infinitely many Markov triples, and they are all coming from evaluate elements of cluster algebra at certain integer values. So let's move on to next one. Next motivational example, also coming from number theory, called Fermat numbers. Okay. So Fermat gave a conjecture that if you take n, you cook up this number fn, where n raised to the power 2 to the power n plus 1 is prime. So that's his conjecture. Right? He said that fn is prime. Fn is prime. So you can check. Let's see, what is f1? F2 and so on. So f1 is 5, f2 is 17. These are certainly prime numbers. But you do f3, then it's going to be quite large. Today we can check it easily, but back in the day, in the 17th century, it's kind of hard to check for higher n. So it was conjecture. But then came along Euler. I'm not sure my pronunciation is correctly, but Euler tried a counter example where f5 he decomposed f5 into a product of these two integers. Yeah. So Fermat conjecture was wrong. Fn is not primes for n for integers n. Yeah. So how is this related to cluster algebra? Well, the counter example of Euler can be realized using cluster algebra. We realize using cluster algebra. Specifically using cluster algebra of geometric type, which is what I will go over in the next slides. Okay, cluster algebra of geometric type. Okay. Any comments or questions so far before I go to the next slightly technical slide? So from here on, it's going to be a little bit technical. I apologize for that. Okay. All right, cluster algebra of geometric type. So I fix a positive integers in. This should be singular, no s there. Fix a positive integer in. Okay, and I fix the following data. Okay, I have the following data where x is an n tuple of variables x1 to xn, and I have an integer matrix. Okay, integer matrix. Bij's are integers. It's an n by n matrix, and it's skew symmetrizable. Okay, what I mean by that is I can find a matrix D, a diagonal matrix D, where the entries are bigger than 0, also integers bigger than 0. Okay, where B times D is a skew symmetric matrix. Okay, so that's what I mean by skew symmetrizable. Right, so I have this data. I fix an integer n. I have this data. So now I would call a pair xb a seed. Okay, I would call a pair xb a seed if the set x1, xn that I choose form a basis for an algebraic field extension of degree n of the rational numbers. Okay. So what I mean by this is just basically this here form a basis for Q x1 xn. Okay, I don't have to take precisely x1 xn, but I can take any elements in this ring of rational polynomial over rational polynomial in terms of x1 xn. Okay, form a basis for this. Anything. Oops. There you go. Okay. Okay, so that's what I meant. So a pair like that, right, where X with this condition is form a basis for this ring, and B is a skew symmetrizable matrix. Okay. Then I call such pair a seed. And this variable xi, I would call the cluster variables. Xi would be called cluster variables, and B would be called exchange matrix. Okay. B would be called exchange matrix. Right. And for each k from 1 to n, for each k from 1 to n, I would define a rule. I misspell here, it's been m. A mutation at k. Okay. What is mutation at k? It's a process that would give you a new seed from a given seed. Okay. If I start with this seed xb, then if I apply a mutation at k to xb, I would get a new seed. Okay. So that's what mutation is for. Is to produce new seed, new x, new b. Okay. New pair x prime b prime. Okay. So how do I define this mutation precisely? It's like this. Okay. Okay. So I denote mutation to be mu k. Mutation at k we denote by mu k. Right. So mu k of b is a new matrix with entry b ij prime, where if I or j, the index, is same as k, then I just negate bij. Right. Otherwise, I would have to add to bij this new constant. Yeah. This is absolute value of bik times bkj plus bik times absolute value of bkj divided by 2. Okay. It's straightforward to check that why is this still integer. Here you divide by 2 here. You can check this quite straightforward to check that this is an integer. Okay, so mu k of b is still a integer matrix and skew symmetrizable with respect to the same matrix D, the diagonal matrix D that earlier I mentioned. Okay. Okay. And for you mutate the variable xk, if k is not, if you mutate xi, I is not k, it stays the same, no change, no mutation for xi if I is not k. But at xk, you mutate xk at k, then you have this formula. So this is not very intuitive, but so let's see an example where this is used. Okay. It's a theorem to say that mutation of a seed is again a seed. Right? That means you mutate b, you still get back a skew symmetrizable matrix with respect to the same diagonal matrix D, and you mutate the basis, you still get a new basis for the ring of rational polynomials. Okay. And mutation is involution. It's an involution. I mean, if I mutate at the same value k, right, at k twice, then I get back the original. All right, let's see an example of a cluster algebra of geometric type. So in this example, I would do a very small example of n equal 2. Okay, n equal 2. So I start with the initial seed where my cluster variables are x1 and x2. Right? It certainly is a basis for this rational ring of rational polynomials. Okay, I just pick the generators. And my exchange matrix B is this guy. In this example, B is skew, not just skew symmetrizable, but it's skew symmetric. So the diagonal matrix D is the identity matrix. Right. So I start with this seed. So let us apply mutation, right, to this seed. So I only have two choices. I can either mutate at 1 or mutate at 2. Okay, so let's mutate at 1 first. If I mutate 1 first, I get this. Okay. So mu1 of x is this. Remember, if xi, where I is not equal to 1, it stays the same. So the only thing that changes is when I is 1. Yes, so mu1 of x1 is x1 prime, where x1 prime is this guy. Okay. So now if you recall the formula earlier, what do you do to get this? You use that formula. What does this formula say? So you say that you look at so here's mu1. So I looked at the first column 1. Look at column 1 of B, right? Column 1 of B. And I look at the entries which are bigger than 0. There's no entry in column 1 bigger than 0. So that remember there was two products in the formula. First product, 2 products, right? First product taken over entries in the column 1 which are bigger than 0. The second product taken over entries in the column 1 which are less than 0, right? So I looked at column 1. Right? There's no entries that is bigger than 0. So conventionally the product is 1. Okay, so that's why I got 1 here. Okay, right? That's the first product. The second product is taking over entries which are less than 0. There's one entry less than 0. That is the second entry, 2, 1. The entry 2, 1. So I raise my x2 to the negation or the absolute value of that entry. So x2 raised to the power 1, which is x2. That's how I get this. Okay, so x2 coming from the second second product, right? And then you divide everything by x1. Okay? Right? So this is what you get for mutating mu1 of x1. Okay? Okay. And then x2 stay the same because 2 is not equal to 1. Okay? Then you mutate the matrix B, you would get this. So basically, you just change the minus sign on the opposite diagonal entries. Okay? So now your new seed after you mutate at 1 is this seed right here. This is the new seed. Okay? 1 plus x2 over x1, x2, and the matrix is the negation of the matrix B. Right? Okay. So now what happens if you mutate again at x2? Right? Remember, mutation is an involution, so I cannot mutate at mu1. I cannot take mu1 of this seed again. Right? If I do that, I would get back to xb. Okay, so therefore I have to apply mu2 to this new seed. Okay, apply mu2 to this new seed. That's what I do here. I apply mu2 to the seed that I just got. Right? This is the seed I got just now. I got that from xb by mutate at mu1 at 1. Now I apply mu2 to that. I would get this. Okay. Okay. And I do it again. So here's mu2. Then I have next one I want to mutate. I have to mutate at mu1. Okay, apply mu1 to the seed I recently got. So apply mu1 to that, I get this. Okay. So here, we go back a little bit. So here, if I mutate at 2, I mutate this one at 2, then the first one stay the same. The only thing changed is the one in the second position. This one changed. X2 is now this, right? Now I mutate at 1, right? Mutate at 1, then this one stay the same. This one is changed. This one changed to this. Okay. Now I mutate at 2 again, right? Here is mutate at 1, so now next one I will mutate at 2. Mutate at 2. And now I get this. Okay, mutate at 2, so then this guy stay the same, Mutate at 2, so then this guy should change, and it's changed back to x1. Okay. Now you can kind of see the pattern. Okay. Let me do one more mutation, right? Here I mutate at 2. Next one I should mutate at 1. Next one I mutate at 1. Then I get back the original seed. Although the order is swapped, but that doesn't matter. Right? This is the original seed. This is equal to xb. I get back the original seed. So this is a cycle. Okay, this is a cycle. And if you recall from the first example of a freeze pattern, where d1, d2 is equal to 1, 1, this is that. This is that. Okay. Right. You take the Z subalgebra of Qx12, the ring of rational polynomials over Q, that generated by all the cluster variable, right? All the cluster variable I got here. So this one, no. Oh yeah, this one, and this one, and this one, right? So this is all the cluster variables that I got from all the mutation I have here. Okay. If you take those cluster variables, right, these are Laurent polynomials in term of x1, x2 over the integers. You take those Laurent polynomial. You generate a Z subalgebra over the ring of rational polynomial over Q, and that is what you get for that's an example of the cluster algebra. Yeah. And this cluster algebra is the same cluster algebra that I mentioned during the example of a freeze pattern where d1, d2 equal 1, 1. And going back to the Markov equations, if you take the exchange matrix to be this one, this 3 by 3 matrix here, this is also skew symmetric. So the skew symmetric is skew symmetrizable, right? So this matrix B here, you start with this matrix B, right? Then your cluster algebra would give you the solution for that Markov equations. Okay. So in particular, what I mean is your initial seed will start with x1, x2, x3, and then this exchange matrix. Okay. And then you mutate this cluster variables, right? x1, x2, x3, in any way you want. You can mutate at 1 or at 2 or at 3, doesn't matter. Right? Then you will get a new seed. Okay. Right. Then you evaluate that new seed at x1 equal 1, x2 equal 1, x3 equal 1. Remember, 1, 1, 1 is a triple Markov triple, right? So if I evaluate my new seed where at x1 equal 1, x2 equal 1, x3 equal 1, then I would get a new Markov triple. Okay. So it's turned out that all the Markov triples coming from evaluating the seed of the cluster algebra corresponding to this exchange matrix at the initial at the trivial Markov triple 1, 1, 1, 1. Okay. So essentially, any solution to that equations, that Markov equation, coming from cluster cluster variable of this cluster algebra. Okay. So quite interesting. Cluster algebra is used there. So now I will, the last minute here, I would mention my research interest in all this is I'm very much interested in cluster algebra, but not just that. I am interested in quantum cluster algebra, which is the non-commutative version of cluster algebra. Okay. So cluster algebra was a sub-ring of this guy. This guy is a commutative rings. And what I want is a non-commutative version of those. Right? So what things I work out with is the non-commutative version of that. And we call it a quantum cluster algebra. And one of the things that we are currently working on is to making a bridge between a cluster theory and non-commutative ring theory using non-commutative invariant such as discriminant, right? And a theory of cluster algebra in a root theory settings. So this is a joint work with Milan Yakimov at LSU and Kurt Tremper at Notre Dame. And some of the reference that I use for this talk is coming from this paper, this introductory paper by the creator of the subject. These two are the creator, and this is a very well-known expert in the field. So I'll stop here. Yeah, thank you very much for listening.
Thank you very much, Dr. Nguyen, for an interesting talk. All right, now it's time for discussion. Do you have any questions for our speaker? Yeah, I don't hear any question. I have a question. My small question like this. So like in one of the last slides, you show the mutation, right? And then you use a matrix. It seems like it is a recursive relation. Like, you know, for example, if you have a Markov triple, right? So Markov triple means, you know, like a tree, you create different numbers, right? In that trees. And so each time you use the matrix B to mutate, and maybe that means to generate those numbers in the tree. Is that correct?
Yes, yes. So all the Markov triples form a tree. Yes, yes. And every time you mutate, you get to a node on that tree. Yes.
Okay. So basically, it's what we do in linear algebra, right? For example, if you apply n times, you know, matrix multiplication, for example, you know, B, right? In your slide, you have B. It's 3 by 3 matrix. So you want to determine the node somewhere in the tree, so you have to apply, you know, like n time, right? And you have to diagonalize the matrix and then use, you know, unitary diagonalization. And then that is similar to the case of Fibonacci sequence. Is that correct?
It might resemble that, but it's not the
yeah, not exactly, but I feel like it's very similar to that, because for Fibonacci, yeah, we have only a sequence, but you know, like recursive relation is based on 2 previous elements, and here you use 3 previous elements, right?
I see. Let's see.
I know we have triple Fibonacci sequence. We have triple.
I see. Well, I wouldn't say mutation is recursive, because you can start any initial seed. You can start any initial seed. That doesn't need to be. You can pick any. Okay, take the ring of rational polynomial over Q, right? You can take any basics for that ring, basically, to start your initial seed.
Yeah, so I see like you do mutation, but not necessarily for the whole triple, just for an element in that triple is also okay, right? So I think that is the difference. Because you say, yeah, you pick, you know, x1, x2, x3, and then you do mutation for x2, for example, x3, not necessarily for the whole 3 numbers.
I know, yeah. Every time you mutate at k is either 1, 2, or 3. Yeah.
Yeah. So yeah, that is interesting. Yeah. All right. Thank you. Okay. Last call. Do you have any questions for our speaker?
I do. I have a question. So are these cluster algebras related to Grassmannians?
Oh yes. The coordinate ring of Grassmannian is an example of cluster algebra. Yes.
The coordinate ring.
So Grassmannian is a variety.
Something. Interesting. Okay, can you try again, Russia?
Yes. If you add a basis to a Grassmannian, you get a differential manifold. So in that way, are cluster algebras related to Riemannian geometry in any way?
It does. Cluster algebra relate to as I mentioned in the beginning in application, technical theory. Yes, very much so. Yes.
Okay, thank you.
Yeah, thank you.
Yeah, very.
Is there anything else?
The application of cluster algebra is very deep. It's virtually everywhere, even in the applied math, in probability theory too. So very far-reaching subjects.
Yeah. All right. Yeah. So if you don't have anything else for our speaker, please thanks the speaker again for his interesting talk.
Thank you.
Okay.
Thank you very much for the opportunity to present, and thank you for attending the talks.
Yeah, thank you everyone for joining us. So next week we have the last talk for this season. So in this semester we have 10 talks overall. So this is the 9th one. Next week we have the 10th one, and when we close the semester. Thank you very much again for joining us, and yeah, have a great day.
Thank you.
Thank you.
Thank you.